Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective. This is lecture number 15 and we will be today looking at some applications of MOSFET. We will start with Y parameter, which where we left in the previous case, and then we will see its application as a switch and an amplifier. So, let us look at the generalized Y parameter model, and as I discussed with you, ym times VGS will give you the value VGS multiplied by YDG minus YGD, right. Now, this gives you the total value which comes out there for generalized value is times VGS minus minus YGD into VGS, right. So, YDG means gate with respect to drain and then drain with respect to gate we will get. So, if you open it up, I will get del ID del VG, right, into VGS or fine, minus this will be del IG times del VD in terms of VGS. So, this gives you the parameter which helps you to find out the current flowing between source and drain because of the change in the gate voltage, and this one gives you the change in the current because of the change in the drain voltage, right. And if you add those two together, you will get the net effect will be available to you in this case. Similarly, if you look at YMB is this part which you see, that is multiplied with VBS, bulk body to source potential, that gives you the current source between body to bulk. And you also have YSD, which is basically 1 by RSD, and that is the reason you see it is negative sign because it is source with respect to drain, right. If it would have been YDS, then it would have been a positive quantity. Since I am reversing it, the direction of current is reversed, the current, therefore, it is a negative sign where it is attached to it. So, I have this negative sign coming into picture in this case. Let us look at therefore, what is Y. So, what is YGD? YGD is this one, this is the YGD value which I was referring to. It is basically between gate and the drain potential. So, this is my gate potential, right, and this is my drain which you see. So, the admittance between them is basically Y minus YGD. If you look at the other way around, it is YDG with a positive sign. Similarly, if you look at this one, this is between gate and source. So, this is your source terminal. Minus YGS basically means the rate of change of the gate current because of the change in the source voltage, right, that is YGS. Similarly, if you look at YBS, which is the second one, it is primarily the change in the bulk because of the source potential change with the negative sign, of course. And if you look clearly, this gate to bulk, right, if you look at this expression here, gate to bulk is basically the so source is generally grounded. Now, if your bulk, you are applying bias, that will result in there might be a current between source and bulk because there is a potential difference, and if you can overcome the depletion region barrier, there can be current. That current contribution is given by YMX times V gate to bulk. Now, YMX is given by this fundamental principle here, which is YBG minus YGB. Why if you look at all these three Y parameters which are shown here, it gives me the difference between the YBG minus YGB, right, and the reason is they might not be symmetrical in nature. And what is the reason for that is that, so what is Y, for example, I will give an example. Let us look at, let us say, YBG. What is YBG with respect to the change in the bulk to gate, right, body to gate change, right. So, if you change the gate bias slightly, how much your body current is changing is YBG, and YGB is when you are changing your bulk potential and your gate current is changing, that is defined as my YGB, right. And they might not be symmetrical in nature because the MOS device, though is symmetrical laterally, might not be symmetrical in a horizontal sense, and as a result there might be a difference between these two values. The net difference which you come out is basically referred to as YMX, right. And this gives you a more than a decent Y parameter extraction values for the general Y parameter model for a basic MOSFET, useful for when you do an admittance matrix. Let us now come to high frequency MOSFET model, right, and let me take into consideration all the other explanations and we will go one by one. So, again I am taking as a 4 terminal device, we have a gate, drain, source and body. So, let us start from the gate and let us move towards the body. So, if I have a gate, then I have the CGS, gate to source voltage, which is between this point and this point. Then you have a between gate and drain, you have CGD, gate to drain capacitance. So, what are these capacitance all about? So, this is something like this, that if your gate is overlapping in this manner, right, this is your gate, this is source and drain, n plus n plus. If this is even grounded and you are applying a bias here, a positive bias, and this is also grounded, then CGS is gate to source, this is gate to source, this is gate to drain which you see here. So, this is gate to drain, gate to source. We have source to bulk, right. So, this is source to bulk, then you have drain to bulk, which is this one, drain to bulk, and these are all, please understand, intrinsic capacitance. I am not considering any extrinsic capacitance at this stage. Then you have this GM VGS, which is basically the current source in the inversion region. So, my GM times VGS is the current source, right. So, current source where for the MOSFET. And what is GMB VGS? GMB VBS is basically the current source because of the back gate which you see. So, I get this and I get this, right. They might be opposite in nature, but that does not matter at this stage, they might be in the same direction, it does not matter at this stage, we just show it by the arrowhead and we show them that to be in the same direction currently. Then we have this RO. RO is basically the resistance between drain and the body. It is effectively the output resistance being offered by the device. So, R0 or R0 is basically the output resistance, right, output resistance of the device. This is the output resistance of the device. So, I have 1 capacitance, 2 capacitance, 3 capacitance and 4 capacitance. So, there are 4 cap, right, there are 2 current sources and there is 1 resistor at this basic high frequency model. Now, if you remember, I was also discussing in my earlier lectures, if you look at XC, which is basically the reactive capacitance of a capacitor, it is 1 by j omega c, right, and for XL, just for information, is equals to j omega L, where omega is the frequency, right, and j is a vector which is an imaginary quantity. Now, if C is the value, now at high frequency this omega becomes very large at high frequency, correct, and as a result what you will see that Xc will fall down. Xc falling down primarily means that you are trying to short the device, right. So, at very high frequency, relatively of the very large order, you might see shorting of these capacitances at a later stage. With this basic idea, let us come back to this expression here. So, CGD is here, CGS is here, we have R0 here and we have CDB here, drain to bulk, drain to body. So, if source and body are shorted with respect to each other. So, if source and body are shorted, if they are shorted, then we get this expression that CDB equals to the CDB value comes out to be same as your because source is CDB will give you CDS the same value, because source and bulk are grounded, and that is the reason I replaced this by CDB here at this stage. Quite interestingly, I have removed here, remember, GMB VBS, because bulk to source, because if bulk and source are shorted, then the value of VBS will be equals to 0, and therefore, GMB VBS will have no contribution in the overall current in the device itself, and that is the reason this current source has been removed, right. It has been removed in the subsequent diagram here. Okay. So, this is the high frequency model of a MOS device, keeping in mind all these important things. Now, one very important figure of merit for a MOS device when you actually want to do, especially a analog design, when you are trying to do, is basically unity gain frequency. So, we try to find out where the short circuit current gain of a common source configuration becomes unity. So, if I am able to find out the output current with input current being with input current, the ratio of that, where the output is basically shorted. So, the output terminals, these two are the output terminals of a 2 terminal network. I am shorting these two together. When I am shorting it, I am trying to find out the value of the output current, and I am dividing that by the input current. The input current is basically this current which you see here, right. This is the input current which I am forcing here, and I get an output current I 0, and I 0 by I 1 will be equal to this one. Now, you will obviously ask me why this ratio is known as a unity gain, because if when I get I 0 equals to I, if you we will see later on that as you change the frequency of the operation of the device, of the input signal, right. This is my input signal. As you change the frequency of the input signal, the gain starts to vary, right, and the gain is not constant, it varies with frequency, because you can understand why, because this we have discussed just now, that as the frequency changes, some of the capacitors become short, as the frequency goes low, some of the capacitors become open, and inductors become short, because if you remember, I was discussing with you that an inductor is equals to j omega L. So, at omega equals to 0, when you have a DC bias, XL will be equals to infinity, right. So, will be equals to 0, sorry, and at omega equals to infinity, XL will be equals to infinity, whereas it is just the reverse in case of capacitor. So, capacitor will be 0 when your omega equals to infinity, right, and when omega equals to 0, your XC will be equals to infinity. So, when you have a DC bias coming into picture, obviously it will become open circuited, and when you have an AC signal, high frequency AC signal, the value of XC will go to 0. And since these two parameters, though inductor is not here in this model, but all these parameters tend to make the gain vary, right. They tend to change the gain from a low value to a high value, and so on and so forth, which results in the fact that we need to find out that frequency, or we need to extract that frequency where the current gain at least becomes equals to unity, and that is defined as the MOSFET unity gain frequency. Let me therefore come to the current expression here, and the current expression is given by Gm times Vgs. This current is primarily flowing. So, this is basically Gm times Vgs, and this is the current which is flowing through the device, where Gm is basically the transconductance of the device, which is del ID del Vgs, is the current flowing through the device when you have a small signal being attached to it, and the next part is basically Cg times dVgs. So, this expression Cg times Vgs, right, is basically the if you multiply this with S as well, then this is basically the current which is flowing because of the so this part, the second part, is primarily because of the oxide layer which happens to generate a charge below the silicon dioxide interface, because of which you do have a charge contribution of Cg times Vgs, right, and that if you multiply that with S and other parameters, you will get the current, right. Now, if your gate to drain capacitance is small, then this can be neglected, and you will have I 0 equals to Gm times Vgs. What is gate to drain capacitance? Remember, gate to drain capacitance is basically the this one, if you look carefully, is this one basically, right. This can only happen in one of the category. It can only happen when you have a large amount of overlap between gate and drain. If the overlap is not there, let us suppose, and you do not have your VG your value of CGD is relatively very small, I can afford to neglect it and I will get the total current to be equals to GM times VGS. Uh, why do you get CGD, gate to drain? Because you actually see an overlap between gate to drain, right? And this is basically an intrinsic capacitance which is between the gate and the drain through the oxide layer, right, and that is what is defined as it. Now, for example, if you take the doping concentration of the drain to be relatively low, then the extension of the depletion region towards the drain side will be larger, and what you will see is that your CGD will increase, whereas if your doping concentration is higher, your CGD will go down as you move towards overlapping is there. And so, depending upon the doping concentration, depending upon the structure of the device, you will actually vary your I0 value. Let us look at VGS, which is given by this expression here. I am not deriving it in the class, but VGS is given by input current divided by S times CGS plus CGD. The same rule applies here, that if you take CGD equals to 0, the second quantity vanishes, which is this quantity vanishes, and you are left with input current by SCGS. And if you look at the output current, right, output current is so this ratio of output to input current is given by GM times CGS plus CGD. But the problem is that in most of the cases, these values of CGS, CGD as well as GM to an extent vary with respect to frequency. So you cannot consider this to be a constant value, but it might be varying as you move from a low frequency to a high frequency region. Now, we define this term Ft as the unity gain frequency here, or transit frequency, and is given by Gm by 2 pi CGS times CGD. Again, I am not deriving it in the class, but as you can see, higher the value of, so the higher the value of Ft, which is this one, the better the device is as an amplifier. So, if you want to use MOSFET as an amplifier, a good way to do that is to increase the value of Gm. When you increase the value of Gm, you effectively mean to say that for the same change in the input gate to source voltage, you get a larger change in the output current, and therefore, the sensitivity of the device is larger, which effectively means if the current is large, the current multiplied by the resistance in the output will be also large, and therefore, my gain will be large. When the gain is large, I automatically say that my amplifier will work in a much better manner as compared to the previous case. So, this Ft is equals to Gm upon 2 pi times CGS times CGD, and we write this to be as omega here. So, omega t equals to Gm times CGS plus CGD, right. So, why omega is equals to 2 pi Ft is omega t, and therefore, 2 pi would actually go down here, and that is what I have written here. So, omega t upon 2 pi, and this S is basically j omega. You can also write as Laplacian operator, which we use for the case of a basic MOS device. Okay. Let me come to the frequency response of a common source amplifier, right. Though I will not be dealing too much about the common source, but let us see how does. So, this is the first sort of an application domain of MOS device which I am showing it to you, and I want to appreciate the fact that the very fact that if you look at the left hand side, so if you look at this expression, if you look at this y axis, this is your y axis and this is your x axis. The x axis is the frequency axis, this is basically in log scale, this is log scale, and this is a dB in dB. So, it is a y axis is in dB, drain the gain is shown, the output voltage gain. So, output voltage upon input signal is defined as my gain and is shown in dB. Right. So, it is 20 log V0 by V in, which you already know, right. So, this is your V0 by V in, which you see. So, it is V0 by V signal, V signal is the input signal which you see. On the right hand side, so I am plotting this, and the overall takeaway from this graph is that as the frequency varies from a low to high value, you can see that first of all the gain starts to increase, becomes constant over a period of time, and then it goes on decreasing. Let me explain this with respect to the figure to the right. This is basically a common source amplifier, right. So, I have this a MOS device here, I have this this is my output resistance, this is a current source which is feeding the MOS device. I have this source capacitance, I have these CC2 and CC1. CC1 is referred to as a blocking capacitor and CC2 is referred to as a CC1 is a blocking capacitor and CC2 is basically your coupling capacitor. So, this couples with the next stage of the amplifier, and basically CC1 actually blocks any DC component of the input signal into the MOS device. So, primarily what we do is that this MOS device is actually biased in the saturation by applying an external DC source. When you apply an external DC source, you ensure that this MOS device is in the saturation region, and then superimpose on that you do V signal, which you see here, this V signal. However, the V signal cannot always gives you pure AC signal, there will be some DC component. So, to block the DC component I put CC1 here. Once I do that, the DC component is blocked and only AC component is allowed through it, and that is the reason CC1 is known as a DC component. Whereas, if you look at CC2, CC2 is basically a coupling capacitor which should ensure that any AC component which is generated from this common source amplifier should move forward, and any DC source or any DC component should be blocked and should not affect the bias of the second common source amplifier. With this knowledge, what we do is that we vary the frequency here and we try to extract the value of the voltage here. Now, when you plot V0 by V6, we get this type of effect. And it is quite interesting, we divide the whole thing into 3 range. I have a low frequency band, I have a mid band here, and I have a high frequency band here, right. So, I have a low frequency, mid band and high frequency. Now, if you look very carefully here, if you let's start from high frequency band. In the high frequency band, as the frequency goes on increasing, as I discussed with you, x of CGS and x of CGD will be all by j omega CGD, and this will be 1 by j omega CGS, right. This will be CGD, this will be CGS. Now, as the frequency goes on increasing, the value of your XCG and XCS both goes on decreasing, correct. As it goes on decreasing, CGS and CGD goes on decreasing, the gain starts to fall down, because so basically what happens, this capacitor starts to short, and as a result this capacitor shorts, and therefore the gain starts to fall, which you see here, the gain starts to fall. Similarly, the gain for as you due to the combined effect of CC1, which is this one, then CS this one, and CC2, the gain actually falls off with lowering the frequency as you in the low frequency band. So, as the frequency starts to reduce, the resistance offered by these capacitors starts to increase and the gain starts to fall down, as you can see. Somewhere in the middle, these two balance each other, and the gain is constant, as you can see here, this gain is constant. So, this is 20 log of gain which I am showing, and this basically is constant gain which you see. We define the bandwidth from FL to FH, where there is a 3 dB drop in the gain, right. So, this drop in the gain should be 3 dB, I match the frequency there, the difference in FH. So, if I look at FH minus FL will be my bandwidth, right. So, if basically means that if, let me draw for you another graph here, let me draw like this. If this would have been like this, and if my 3 dB would be somewhere here, then basically what means that the bandwidth actually increases. So, one wonderful formula which comes out is bandwidth multiplied by gain is always constant. So, basically it means that if you have a large bandwidth, automatically your gain drops down. Similarly, if you have a higher gain, then the bandwidth actually is lower, right. The bandwidth is difference between this FH is known as high cutoff frequency and FL is the low cutoff frequency, right. And this is where you define the voltage gain to be equals to this. Now, if you look very carefully, if the output current by input current is 1 and you are trying to do in dB scale, then 0 dB will be the gain where output current by input current will be approximately equals to 1, and any 3 dB drop from there will give you the bandwidth in terms of power. This is also referred to as a half power point, where the power has actually dropped to half its value from the mid band gain in a sense. This is an overall frequency response of common source amplifier. So, as I can tell you, the gain is almost constant over a wide frequency band, and that is known as a mid band, and the mid band gain is given by this formula. I am again not discussing all these things with you. So, this is GM times GM times RD is the overall gain, and therefore, the RD is broken down into RG plus R sig, where R sig is basically the signal source resistances, right, and that multiplied by effective value of the transconductance is given by this formula, right. So, it is basically 1 by GM times RD times RL, right. The 3 dB bandwidth is given by FH minus FL, and we define the bandwidth to be approximately equals to FH if FH is much larger as compared to FL. So, you understand, if FL is the order of few hertz only and FH is the order of kilohertz, the bandwidth will be of the order of few kilohertz, right. So, this is a gain bandwidth product which I am trying to show it to you. This AM is basically the gain multiplied by bandwidth. Gain bandwidth product is given by the product of AM multiplied by bandwidth. So, this is a multiplication sign which is available here. So, what we have done is, in this case, is given you a brief idea about a full circuit analysis course will be actually required to derive all these quantities and explain all these quantities, but this gives you a brief idea about how the mid band gain and the 3 dB bandwidths are related with respect to each other. With this, let me recapitulate what we did till now. And what we did was, at the end of this class, we looked at the Y parameter model. So, we looked at the generalized Y parameters. We looked at the circuit, small signal circuit with Y parameters. Then we went to amplifier design. Within that amplifier design, we looked into a common source amplifier, and we tried to find out the relationship between bandwidth and gain, and how various capacitance play a role in determining the amplification, and the concept of FT, which is the unity gain bandwidth which we see, right. So, this is the overall sort of takeaway from this class. With this, let me thank you for your patient hearing, and we will meet in the next class.